Actually, we have one last topic left in Module 3, Part D, but that topic mainly, it's a problem-solving topic. Yeah. It's a problem-solving topic. Yeah. I will not give you computation questions on that topic, but we may have the concept questions a little bit. Yeah. So I plan to do this way. Because every class, after I post the video, I look at the total time. Still, sometimes I have about 10 minutes. So I plan to use the remaining time after our normal lecture video. Then I use several short videos to complete the remaining part of the module. 3, Part D. Yeah, because then, so you just study the problem solving, mainly the thinking, how to do the logic thinking in problem solving. Yeah. So, all right. So today we start a new module, Module 4, Divide and Conquer Approach. Before I start the lecture, I want to talk about one important thing. We will do quickly the midterm exam. So we will do next week, 1 week from today. So I need to talk about that a little bit. So you need to, start your preparation for this midterm. Yeah. All right. Midterm exam. Yeah. So, based on the syllabus, I let you do it online. Yeah. So to reduce your pressure a little bit. Yeah. So you have more time to work. That means less pressure, right? Yeah. So here I just write the, the dates, the period listed in the syllabus. Yeah. March 19th, Thursday, through March. Yeah. Yeah. So the Thursday, Friday, Saturday, Sunday, okay? Yeah, 21st, 22nd, right? Yeah, all right, 22nd, Sunday. Yeah, so that's the period of the midterm, online, right? Online. Yeah. On Wednesday, we have a normal class. But I try to do it this way, because I try to post the midterm as a homework assignment, Canvas assignment, just like our homework assignment. Yeah. So I will post it after our normal class. So actually the Wednesday night, so you will see it. Wednesday night. Yeah. Yeah. Although here I listed Thursday, but it will be available right after our normal class. Yeah. All right. So the test still Part A, Part B. Yeah. All right. Part A, Part B. Okay. Yeah. Part A, 10 concept questions. All right, yeah, 10 concept questions. Part B, Part B, 15, yeah, 15 computation questions. Okay, yeah. Adding together, yeah, total 25 questions. So the format, I mean the question format, okay? Question format, same as your homework assignment number 1, okay? Yeah. And for the computation questions, basically I modify the computation questions you did in homework assignment number 1. I modify the conditions slightly, okay? Yeah. The topics, yeah, the background, the stories, pretty much, very, very similar, okay? Yeah. So I will not give you, completely new questions. Yeah. Completely new questions. But I need to change the conditions slightly, okay? Here, there, conditions slightly. Yeah. But you still, so you need to completely understand the solutions. Yeah. So I will post the solutions. Yeah. So you need to completely understand the ideas. Then you can modify. Yeah, because we need to modify the solutions, yeah, for different conditions. Yeah. So that's the way we will do for the whole midterm. Yeah. All right. Yeah. So there is an online class. For online class, I will do the same thing. Yeah, because online class, when I post midterm for in-person class, at the same time, I also post for online class. Yeah. So same time period. Yeah. Part A, Part B, same time period. Yeah. Okay? Yeah. Yeah. All right. Yeah. So let's start Module 4, Part A, Insertion sort. 8.1, Insertion operation. So let's look at our old sorting problem again, but this time we need to use a different method. Yeah. Insertion sort. All right. So the strategy we want to take here, start with a simple case. When we start, we start from the simplest case. So then we gradually add more and more elements in the array, and we try to, because here the topic is divide and conquer, right? Yeah. So divide and conquer. Yeah. So here for this one, actually we use the reverse process of divide and conquer. Because divide and conquer, every time we divide the given array, right? Yeah. Here, something like reverse process. We grow the problem size. We grow the problem size. Yeah, yeah. But you can. So here we understand divide and conquer. Yeah. So this is another way. Yeah. All right. Then, so we grow the data size gradually. All right. And how do we grow? Every time we increase the size by 1. Every time we just add one element into the. Yeah. So when we grow, usually we grow the size, grow our array 1 by 1 element. Yeah. When we do divide step, yeah. So we have many different ways to divide, right? Yeah, yeah. Yeah. But when we grow, mainly we grow 1 by 1, adding elements. All right. How to connect two adjacent cases? Here, Because when you grow by adding one new element, the previous solution and the current solution, there is a small gap between those two adjacent problems. The problem with sizes with one difference. So we need to consider how to bridge the gap between those two adjacent cases. All right. So let's work on the problem size. Now, here. Now, let me draw a diagram to show our idea. Visual understanding. Let's do a visual understanding. When we start with an array with only one element. That's the simplest case, right? Yeah, because we need to start with the simplest case first. Yeah. One element array, we do not need to do anything because it's ordered array. Yeah, so we treat one element array as an ordered array. So no problem. Yeah. Now we need to consider. Now we want to add a new element, A1, into our current ordered array. Yeah. Our current array is ordered. Now we need to add new element A1 and put it at the right place. Yeah. A1 could be greater than A0, could be less than A0. So we need to make our decision where to place A1 element. Before A0 or after A0. So we need to do one comparison. One comparison, we can answer that question, right? Where to place A1 element. Yeah. In other words, by one element, we get the current array sorted. Yeah, because current array, two elements, right? Current array, two elements. So one comparison. So we get a current array sorted. Yeah. So now, and the next step, this is an ordered array. Okay? This is an ordered array. All right. So this is the starting point of our next round processing. Okay? Next round, we get a new element A2. Now we need to determine where to place this A2 element in the currently ordered array. Right? Yeah. Yeah. So, can you tell me how many comparisons do we need to get this A2 element placed in its right position? Put it in place. 2. Yeah. Yeah. But the 2, can you tell me, is the best case or the worst case? Worst case. Yeah. Worst case. 2. How about best case? 1. Yeah. 1 best case. 1 comparison. Yeah. You compare A2 with A1 and you see A2 is greater than 1. Then you're done, right? So that's the best case. Worst case, yeah, so A2 less than A1. Yeah. Here we can also assume distinct elements assumption. Yeah. Because make our life easier, right? Yeah. Distinct. Yeah. In our first round consideration, let's assume all the elements are distinct. Yeah. Later, yeah, after we find a solution, then we can remove this assumption, right? Yeah. Yeah. So it's okay. We can assume distinct element. Okay? Yeah, distinct, yeah. Yeah. Next. Yeah. All right. Keep going. Yeah. So here, I think after these 2 small experiments, we get an idea, right? What should we do? Okay? Yeah. Yeah. we can consider a general case. Yeah. General case, but our current array is ordered. Yeah. So here we can assume our current array must be ordered when we add a new element to a currently ordered array. We need to do some work. Okay? Yeah. Yeah. So this kind of work, we put a new AK element in place, right? Yeah. In place. So that process, yeah. So we treat it, yeah. That process, we treat it as a, insert an element in a sorted array, yeah, at the right position. Yeah. So here, this insert step, insertion, yeah. This step. So we need to study this insertion step. All right. Yeah. So next, let's study the insertion operation in this whole sorting process. Now, we want to understand, because this is the main operation in the sorting. Yeah. All right. Here, now, when we study insertion, shift elements for insertion. The details in insertion, a lot of details we need to consider in the insertion operation. All right. Now, so how to see that? So let me use a diagram to show you, yeah, how to see the details. Yeah. Here, the currently ordered array is arranged. So here I draw a list of locations. Yeah. So that means because they need to be stored in consecutive locations in main memory, right? Yeah. So here we can understand. So these elements are stored occupying consecutive locations in main memory, computer main memory. Yeah. We know array elements are always stored in consecutive locations in main memory. Yeah. All right. Now, when we insert a new element, we cannot break that rule, right? Yeah. Consecutive locations, array elements must occupy consecutive locations in main memory. We need to preserve that rule. All right. So then here, we need to find the location for this new element, right? Yeah. New location for AK element. Yeah. And we need to make arrangement. Yeah. We need to do something, do some work to prepare the new location for this new element, right? Yeah. So that's our visual understanding. But how to do that preparation? Yeah, here. All right. Now, so because we need to consider all the necessary details in this process. Yeah. And inside computer main memory, here. So that's why we need to have some small background in computer memory understanding. All right. Yeah. When we start, yeah, because when you start, this AK element has its original location, right? Yeah. So this dashed box, this is the original location of this new element. Yeah. All right. So now we need to find a new location for this AK element. All right. Yeah. So what do we need to do? We lift AK from its older location to a temporary location. Yeah. So after we lift it, we need to store it in a temporary location, right? Yeah. Yeah. So here's in our mental experiment. We do this mentally, right? Yeah. So not in the coding. Yeah. So here it's different from our coding. So not there yet. not the coding step yet, because only after we find the whole solution we can do the coding, right? Yeah. So here still the mental problem solving stage. Yeah. All right. So we need to lift it to a temporary location for that AK in our mind. All right. Yeah. After we lift that AK, then this location is available, right? Yeah. That location is available. So we can move other elements to this available location. All right. So the next step, we compare. Yeah. So we'll compare AK with the AK minus 1 first. Do the comparison. Yeah. If AK minus 1 is greater than AK, then we can move it to this available location. Yeah? One position to its right. Yeah. So if AK, yeah, if this AK minus 1 is greater than AK, so we'll move it one position to the right. So we call that operation the shift operation. Shift this element one position to the right. Okay? Yeah? Only one position to the right. But after that shift operation, yeah, then this location is available, right? Yeah. The original location occupied by AK minus 1 is available. So then we can compare AK element with AK minus 2 and see which one is larger. If AK element is larger, then we drop AK element to that vacant location. Okay? If AK minus 2 is larger, then we shift it to that one position to its right. Yeah? So in this way you can see, yeah, so we keep doing comparison and shift operation. Yeah, we do comparison first. Then we determine how to do the shift operation. Okay? Yeah. After a sequence of operation, here, this arrow, the arrow here, I want to use this arrow to mark the right position for this AK element. Yeah. So this arrow location, it points to the right position of AK element. Yeah. Suppose the final position for that AK element is right here. Yeah. That means AI minus plus 1 element should be shifted to its right position. Right? Yeah. So this location must be vacant before we drop AK element. Okay? Yeah. Must be vacant. All right. Yeah. Before we drop it. Yeah. So here already. Yeah. So we. Yeah. All right. So the last step, we assume this location is vacant before we drop AK. Okay? Now, all the preparation work has been done, right? Yeah, all the preparation work has been done. So the last step, we drop AK element to complete the whole insertion operation. Yeah, that's all we need to do. Okay? Yeah. This standard insertion step. So this is the standard insertion step. No? No. Now, after you drop AK, this insertion step, now you can write a code. Yeah. So if you need to implement this algorithm, yeah, so based on this understanding, so you can write a code. Okay? All right. But when you write a code, yeah, it could be slightly different from our previous mental experiment. Yeah. So What's the difference part? Yeah, in our mental experiment, we lift AK element to a temporary location. But when you write code, you don't need to lift, right? Yes. Yeah. So you don't need, yeah. So you may not need to lift, yeah, because, all right, you just compare AK with, yeah, because that, yeah, so here, yeah, actually, yeah. Yeah, so yeah, so you may need a temporary variable. Yeah, so you may need a temporary variable. The place you need why you need a temporary, because when you move AK minus 1 to AK location, you have to use a temporary variable, right? Yeah. When you move it, when you make the shift, when you move it, yeah. Otherwise, you overwrite, right? You overwrite the value in a AK position. So you need to, store it somewhere. Okay? Yeah. So you can bring it back. Yeah. So after a few shifts, then you can bring it back. Yeah. All right. Yeah. So that's the whole insertion operation. Yeah. All right. After that understanding, after this understanding, so you can see we can get whole array sorted, right? Yeah. Yeah. Because every time when you have a new element, when you do insertion for a new element, you just do the step. From beginning to end, you get a whole array sorted. Yeah. So, all right. Yeah, but here, other than comparison, we also have assignment operation, right? Yeah. So here, some more details we need to consider. Yeah. Because when you do the shift operation, what's the shift operation? That's the assignment operation, right? Yeah. You assign one value to element in a different location. That's assignment operation. Okay? Yeah. So here, so you have comparison operation, also assignment operation. Yeah. So those operations, if we use asymptotic notations, that's a big theta of K. K, that's the array size, right? Yeah. K array size. Yeah. K elements. Big theta here we use big theta, that's the average case, right? That's average case. Because best case 1, right? Yeah. One comparison, right? Yeah. Best case. Worst case, K comparisons. Assignments, assignments, close to K, because sometimes you need to copy to the temporary location. That's also assignment, right? When you copy some element in a temporary location, that's an assignment. Yeah. So, you may need to do one more assignment than the number of comparisons. Yeah. All right. Yeah. So here, next, implementation of insertion sort, and we need to also do the analysis. We need to count the number of comparisons. Yeah. So we treat comparisons as our basic operations, not assignments, although they are very close in numbers. So we count the comparisons. Efficiency, estimate efficiency, compare and shift operation. All right. Yeah, so that's the work we need to do. Compare and shift. All right. Worst case efficiency. So you need to compare AK with all the elements in the currently ordered array, yeah, that's, yeah, because when we start, yeah, so here, well, we look at the growing, in the growing way, the first one is 1 comparison, right? Second one, 2 comparison. For the worst case, 3 comparison. The last one, n-1 comparisons. Yeah, the last one, n-. So you add them up, that's 1/2 times n-1. That's the worst case efficiency. The best case efficiency, yeah, the best case efficiency, yeah, yeah. Here we use asymptotic big theta of n squared. Yeah. So you know the meaning, yeah, n squared. Yeah. All right. But for the best case, each insertion step best case is 1 comparison, right? Yeah. The best case. Yeah. So the best case is n-1. n-1. Yeah. The best you can get. Yeah. That's the big theta of n. Yeah. Now you compare the difference between best case and worst case. What's the difference? From big theta of n squared to big theta of n. How large is the difference? Do you have an idea? N squared versus n. Is that the difference big or not? Very big, right? Yeah. Do you remember? Here, I want to recall. Yeah, because here we need to get some specific feeling about this difference. Do you still remember when we did polynomial evaluation? Right? Polynomial evaluation, brute force method, right? Brute force method, the number of multiplications in big theta of n squared, right? Number of multiplications. That formula, yeah? Big theta of n squared. Horner's rule. Horner's rule. Number of multiplications. This one, right? Yeah. Yeah. So here you can see the difference between insertion sort, worst case and the best case. The same, pretty much the same difference between polynomial evaluation problem, the brute force method, and Horner's rule method, right? Yeah. That difference, yeah, remember? So I use 1 million element to do the comparison. Yeah. 1 million element multiplication. If we use Horner's rule, we need a 1 time unit. Yeah. 1 time unit, we use 1 second. Okay, 1 second. Yeah. But if we use the brute force method, that huge number, 5.8 days, right? Yeah. So you can see that difference is 1 second versus 5.8 days. That huge difference. Yeah. So here, if you want to see how big is this difference, 1 second versus 5.8 days. That huge. Okay. All right. Yeah. So now you can see this is best case. And the worst case difference is so big. This is some very special property of insertion sort. Now, later, when we look at all the other sorts, only insertion sort has this property. Other sorts, the difference between best worst case and worst case, not that big. Not as big as this one. So, insertion sort, difference, so big. Yeah. All right. So this big difference. Yeah. Yeah. Later, we will look at the application from application perspective. Yeah. So we can take advantage of this property in applications. All right. Then average case, not too hard to see. Yeah, because for the worst case, each insertion average case somewhere in the middle, right? So 1/2 of each insertion step, the average case, you do 1/2 of the comparisons for each insertion step. So when you add all these numbers for the worst case, average case just 1/2 of the worst case. 1/2 still in big theta of n squared, right? Yeah. Well, the constant. You multiply 1/2 constant. So they are in the same category. Yeah. Average case, worst case in the same category. Big theta of n squared category. Yeah. Right? Yeah. All right. Yeah. Derive it. Yeah. Yeah. Pretty straightforward. Yeah. All right. Then the last thing, conclusion. Yeah. The conclusion. Yeah. So here, there is one special situation. So now we talk about in the real world application. Because the property we discussed in the previous slide, so special. So in the real world, so we want to look at how to use that property. So then, in the real world, if you see a situation like this, if the given array is almost sorted, sometimes it could happen, yeah, almost sorted, right? Yeah. Then insertion sort is a good choice for sorting data with that special property. Yeah? So if you have the data, so this is your data, have this property, then insertion sort is the best way to go. Yeah. Let me use a diagram to explain this situation. This line segment represents the whole array, but almost sorted. There are some scattered locations. The data in certain scattered locations are not ordered. Yeah. All the other parts are ordered. Yeah. All right. But you need to get all your data ordered by sorting. Yeah. So you need to select appropriate sort, right? Yeah. Yeah. So if you look at all the possible sorts available, yeah, so you will see insertion sort is the best. Will be fastest. Yeah? Because for the ordered part, you take the best case, right? Ordered part. That's the best case, right? Very fast. Then unordered part, then you need to do some comparison. Then best case, right? Yeah, do some work. Best case. And not too much places, not too many places unordered. Yeah. So you can. Yeah, so you can take advantage of this property. But for other sorts, later you will see other sorts. Even if your original array is already ordered, then you apply other sorts, not insertion. So here we look at the sorts other than insertion sort. Still very slow. Okay? Still very slow. All right? So you will see. So insertion sort has this special property. Yeah. Already sorted or nearly sorted. Very fast. Okay? Yeah. All right, so that's the insertion sort topic. Yeah. So we completed. Yeah. All right. Next. Then, this insertion sort is very simple, but this idea can be used in many of our problem-solving questions. No, so this simple idea, is very useful. And when we use the insertion idea in our later problem solving, we need to modify the idea slightly. Yeah, we need to do some modification, okay? So to make it more useful. Yeah. So here, I do some simple examples. Sort 4-element array and sort 5-element array. Okay? Yeah. All right. Yeah. All right. So what now? So to do those questions. All right. Here, when I work on examples, because we need to do many different examples from now on. Yeah. So when we do those examples, yeah, from now on, I want to prepare you for the final exam. Because this module 4, that's the content for the final. Okay? Yeah. For midterm, we don't touch module 4. Okay? Yeah. Module 3, we touch the concept questions. Computation questions, we leave. Computation question for module 3, we leave after midterm. Okay? So, yeah. Module 3, we only do some concept questions. Okay? All right. Yeah. So now, we need to prepare for computation questions for our final exam from now on. Okay? All right. So how do I do the preparation for the final? So here, I plan to do a list of basic questions, problem-solving questions, related to your final problem-solving questions. Yeah. Here, I call it this FBR, okay? Yeah. FBR. F, final. Basic result. Yeah. So these basic results you can use in your final problem solving directly. Yeah. So here we study, we do preparation. Yeah. So we do basic result. Okay, all right. Yeah. Here. Yeah. The first basic result. So number 1, first basic result. Okay, all right. Sort a 3-element array. That's very basic, right? Yeah. Sort a 3 basic element array. Very simple. Yeah. But here, let's practice our insertion sort a little bit. Okay, insertion sort, right? Yeah. Yeah. Solution. So here we use our insertion idea. Okay? Yeah. Insertion, all right? Yeah. So 3M array, let's consider x1, x2, x3. The given array, 3 elements. All right. So our first comparison, x1 and x2. Okay, all right. Yeah. And we can assume, yeah, because x1 less than x2, without loss of generality. Yeah? Because that the other case is just symmetric, right? x2 less than x1, you know, symmetric. You flip, yeah, same thing. Yeah. Yeah. So we want to reduce our discussion. So we can use this way. So in math, it's very common. People use this. Okay? Yeah, make assumption. You know. Yeah. All right. That's the first comparison. After first comparison, our x1, x2 array is ordered, and we need to insert x3 elements to it by 2 more comparisons, right? 2 more comparisons for the worst case. For the worst case, okay, all right? So then, so the conclusion, yeah, very easy, conclusion. Total 3 comparisons for the worst case. Okay, yeah, for the worst case, yeah, all right. Then there is another related question, yeah, because I remember I gave you a concept question. Oh, concept or not? Yeah, whatever. I'll give you a question. Find the median of 3 elements, right? Yeah. So here I can put at the F, B, basic result number 2. Yeah. Number 1 is this sort 3 elements. Find the median. For the worst case, you still need to use 3 comparisons. Yeah. Find the median. Yeah. Some students use 2 comparisons. That's not the worst case. Yeah. So here, let's consider that this question is slightly different. Find the median of 3 elements. All right, yeah. Okay, yeah. Solution. First comparison. Yeah. Because you can do arbitrary first comparison. Okay? Yeah. You pick 2 elements, do comparison. Okay? Yeah. So the first comparison, let's assume after comparison, we have this x1 greater than x2. Yeah, so we draw diagram in this way. The higher one, the larger one, lower one, smaller one. All right. Then, after that, x3. Yeah. So you only have 2 choices. Either x3 with x1 or x3 with x2. Okay? All right. Think about if you do 1 more comparison, you may not find the median. Only 1 more. 1 more, you either compare x3 with x1 or x3 with x2. But only 1. You only have 1 last comparison to use. If you compare with x1, if x3 greater than x1, then you find the median, x1. But if x3 is less than x1, you don't know which one is the median, right? Yeah, you don't know which one. So you need still 2 more comparisons to find the median. Two more comparisons, find median. Then, if you use 2 more comparisons, basically you sort this 3-element array, right? You get the 3-element array sorted. If you sort an array, then the median, you just select the one in the middle. Because you sort it. You sort it. Yeah. Yeah. Now here, one thing, another related question I want to explain here. In general, when you find a median, do you need to sort an array? In general, you do not need. Because you do too much work. If you sort the whole array, that's a lot of work. Unnecessary. So in general, finding the median, you do not need to do the sorting. Yeah. But 3 elements, the array size is too small. Then finding the median and the sorting, basically you do the same amount of work. Same amount of work for 3 element array. Yeah. For more than 3, yeah. So you do not need to do the same amount of work. Finding median versus sorting the whole array. Yeah. Yeah. Later we will see. Later, if we use asymptotic notation. Yeah. So for this question, here I use asymptotic notation to tell you the difference. Sorting, asymptotic notation, yeah. Later we will learn, yeah. Big theta of n log n. Yeah, n log n. Okay, here we're talking about the average case efficiency, n log n. Average case efficiency, n log n. The fastest possible sorting algorithm, n log n. All right, then finding the median. Finding the median. Finding the median, big O of n. Big theta of n. Big theta of n. You know? So difference. Yeah. Yeah. All right. So that's the first 2 basic questions for final. Yeah. All right. Then the third one. Yeah. So here with number 1, number 2. So this here, number 3. All right. Number 3. Number 3. Let's sort 4 element array. Okay. How many comparisons do we need to sort a 4 element array? Okay, all right. Solution. All right. Let's apply the insertion idea. Idea here. All right. Yeah. Yeah. Because we have the experience. Yeah. We have the results from the previous basic questions. Yeah. All right. So let's do this. We use the first 3 comparisons. So here, assume this array, 4 elements like this. All right. Yeah. Use the first 3 comparisons to sort the first 3 elements. Yeah. Because you need to use 3 comparisons to sort first 3 elements. Okay, all right. Yeah. So now I use the diagram to represent after the sorting. Okay, yeah. The first round sorting 3 elements in order, right? Yeah. Yeah. Suppose x3 here, x2 here, x1 here, in order. Okay. Then now we have x4 here. Sorry, x4. So our last step, do we need to do insertion? Insert x4 in a currently ordered array? Yeah. So what do we need to do next round? Basically, we do the insertion operation. Insert x4 into the currently ordered array. Yeah. Yeah. But here, this insertion, yeah. So here I want to pause a little bit, because what we are going to do will be different from our standard insertion operation. You know standard insertion operation, right? Yeah. So you need to understand, in the standard insertion operation, we need to do the comparison following the order, right? Yeah. That's the standard insertion. So here we will do modified insertion operation. We don't do standard, yeah, because not the fastest way. Yeah. So here, yeah. So 2, we need to do comparison. Okay, all right. So standard insertion versus modified insertion. Okay, yeah, so here we do improvement. This step. Yeah. All right. Standard insertion, the typical property for the standard insertion, so that's the sequential insertion. Sequential insertion. Because when you do your comparisons in the standard, you do the sequential comparisons, right? Yeah. Yeah. Following the, right. Yeah, but the modified insertion, yeah, because we feel sequential insertion still too slow. So we will change, yeah, change to a different type of insertion, binary insertion. Not sequential, it's a binary insertion. And it will be faster. Why? Yeah. So you know binary search, right? Yeah. Everyone here, so at least you heard of binary search. You know how to do binary search. All right. So when you do binary search, your data is ordered, right? Yeah. Your data is ordered. So here you can see our data, this part is ordered. If it's ordered, we can apply binary search, right? Yeah. We know binary search is faster than the sequential search, right? Yeah. So here, the same thing. So the binary insertion will be faster than the sequential insertion. All right. So what is the binary insertion? Binary insertion, the first comparison, you compare x4 and x2. Compare the one in the middle, the median element. You compare x4 with x2. Okay? Yeah. So this is your comparison number 4. Yeah? Because you already used the first 3 comparisons. So the next comparison you will use comparison number 4. All right? So after comparison number 4, you have 2 cases. Either x4 is greater than x2 or x4 is less than x2, right? Yeah. These 2 cases. If x4 is greater than x2, you just need one more comparison, right? With x3. One more comparison. Comparison number 5. If x4 is less than x2, you need one more comparison with x1. Still, comparison number 5. See? Yeah. Then, after these 5 comparisons, you can find the right position for x4 element, right? Yeah. You know where to place this x4 element in the currently ordered array. Yeah. So here you can see with the binary insertion, you just need 2 more comparisons. For the worst case, right? 2 more comparisons. For the worst case. But sequential comparison, you need 3 more, right? 3 more for the worst case. So you save 1 comparison for the worst case. Okay? Yeah. So that's the whole idea. Okay? That's the whole idea. Yeah. All right. Conclusion. So we need to make a final conclusion. Okay? Yeah. Total number of comparisons we know sorting 4-element array equals 5. Okay? 5 comparisons. 5. Yeah. The next question is this number 5 is the best we can get? Right? Yeah. Yeah, because can anybody do better than 5? Right? Yeah. So then there is a question. Optimal or not? If this sorting is optimal or not. Okay? So the answer, so here, I'll give you the answer. Yes, it is optimal. Five is optimal. Nobody can do it in 4 comparisons. But how do you see it? Yeah. Later we will have a formula. Yeah. So there is a formula. We can calculate the lower bound for optimality. Lower bound for comparison-based sort. Yeah. Later we will talk about that. Yeah. But here just tell you the result. It's optimal. Okay. Nobody can do it better than 5 comparisons. Yeah. All right. Yeah. Next. Yeah. So let me do the sorting 5-element array, but we cannot complete. But at least we can, do some preparation, right? Yeah. Today. All right. Yeah. So the number 4. Okay, yeah, number 4. All right. Sort a 5-element array. Yeah. So 5 and x1. x1. x2, all right, yeah. So this question actually pretty hard. This question pretty hard. Yeah. So what do I mean pretty hard? Yeah. Yeah. Because for a person without our background, here, yeah. So we build up our background, quite some. Yeah. So probably we can do a little better, but it's still hard, okay? If I give you this question as your homework question, so still very hard. Yeah. Yeah. So for the general people, but they need to have quite some background. We assume some basic math, basic computer science background. So if you have a friend in IT industry, so you can give this question. Yeah. So very hard. So usually people need several hours to find the best solution. So what's the best solution? Here, I'll give you the answer of the best solution. 7 comparisons. Seven comparisons, and this is the optimal solution. Optimal solution. So nobody can do better than 7 comparisons. Okay? Yeah? Nobody can use 6 comparisons to solve 5-element array. 7 the best. All right? Yeah. Yeah. To solve this problem today, so I can, start a little bit. Yeah. Next time we will do the whole thing. So here I can give you the method we need to use. Tournament method. I mentioned it a little bit before. Okay, yeah, here we need to use it. Tournament. Method. We need to apply tournament method on the first 4 elements. Yeah, because we like to do it on power of 2, right? Yeah. So on first 4 elements, okay, x1, x2, the first one. Okay, let's assume x1 is the winner. Yeah. x3 and x4. We assume x3 is the winner, all right? Yeah. Then x3 and x1 and x3, yeah, we can assume x1 is the winner. So here we already used the first 3 comparisons. Comparison 1, comparison 2, and a comparison 3. So this is our round 1. Round 1. Okay? So these 3 tournament comparisons. Okay? Yeah. All right. Yeah. So very simple. Yeah. But we already consumed 3 of the 7 comparisons. We only have 4 more comparisons we can use. Very precious resource. 4 more comparisons. We need to get the whole array, 5-element array, sorted. Okay, all right. Next time, I will complete this question. Yeah. The remaining not too hard. Yeah, actually, won't be too hard. But if you use the binary insertion, it will be much better. Binary insertion. Yeah. So here, from today's class, so you will get a impression that binary insertion is very useful. Okay? Yeah. In many of the following problem-solving questions, binary insertion very useful. All right, that's it.